Right, let's talk about feasibility and the equilibrium constant. Now, there had to be a relationship between the Gibbs free energy, entropy, equilibrium constant, and something that comes later is something called a standard electrode potential. All of these things really are saying how far to the right or to the left a chemical reaction is. Okay? So we've kind of assumed in the past that some reactions go to completion, some reactions don't happen, but we could consider this to be a continuum. So here we've got a relationship that you must learn. You'll need to use this in calculations. Okay, so let's have a little look at what's in it. R is the gas constant. All right, that's not going to change. You don't need to remember it because it's in data books and it's given in the exam, but 8.3 is the value, obviously. T is the temperature in Kelvin. K is the thermodynamic equilibrium constant and has no units. Well, K potentially would have units, wouldn't it? But because it's a log, it's a natural log, ln, then it loses its units, so we don't worry about that. Delta G with a little circle here means that it's the standard free energy change. Okay, and what does that mean? Well, that means free energy change standard conditions. And the standard conditions, obviously, 298 K, 1 atmosphere pressure, concentrations, we'll talk about that, but could be 1 mole per decimeter cubed. So there's some standards there. That's the standard free energy change. Okay. Now, remember that K is only affected, it only changes with temperature. It's a temperature dependent constant. So the classic, it's a constant, but it's not constant because it changes with temperature. Think about equilibria and think about how the equilibrium shifts when you change the temperature. So delta G, forget about the standard, delta G will be different if K is different. Yeah, so the free energy change for a given reaction will depend on conditions. Just looking at this general expression, if K here gets bigger, i.e. if a reaction is further to the right, then ln K gets bigger. This is negative, so it becomes more negative, so delta G becomes more negative. Now that makes sense, doesn't it? For a reaction to go forward, delta G, Gibbs free energy, needs to be negative. So that fits with what we know. Okay, careful, delta G is given in kilojoules per mole, but you must use joules per mole for the above equation. And then we can rearrange that particular equation to make K the subject. Just a little maths challenge for you. Have a go. And it looks like that, doesn't it? Where E is your magic little natural number. Gives you a chance to use that button on your calculator. Okay, relationship between delta G and K. Right, so let's have a look at the Haber process. Now Q here is a quotient. Q essentially is, well, if you think about it, we've always written it as K because we're usually talking about the equilibrium mixture quotient, aren't we? So K is taking account of the stoichiometric coefficients. K would be equal to that at equilibrium. But if it's not equal to that, then the equilibrium shifts in order to restore K. So for example, here, on the left-hand side here, Q is less than K. We've got more of the denominator and less of the numerator. So what will happen? Well, the denominator will make the numerator, the reactants will make the product to try and get K restored. And on this side, we've got too much ammonia, too much in the numerator. So it will shift back spontaneously. It will look for this minimum in this curve. Okay? It's quite fascinating, isn't it? The free energy of nitrogen and hydrogen is up here. The free energy of ammonia is here. So there is a natural tendency for this reaction to go forward and make ammonia. Right? Great. But it's not a linear relationship. And this is the thing that catches people out sometimes. Now, it's a bit beyond A level. But the idea, the basic concept here is that a mixture of ammonia, nitrogen, and hydrogen has got greater disorder than pure nitrogen and hydrogen and pure ammonia. So here at equilibrium, it's the perfect maximum disorder, minimum free energy. If at equilibrium we start making more ammonia, it starts going up this curve. Having more ammonia increases the order of the system and the system's spontaneous tendencies to go back to the minimum. It's lovely, lovely reaction, lovely effect. Okay, this is going back to the idea that it's in a continuum. If delta G for a reaction is very large and positive, then it means that the reaction doesn't happen. Now let's have a look here. If delta G is very big and positive, then the reactants are favored. The reaction doesn't take place. And as you can see, K is tiny, so the reaction doesn't go forward. If delta G is very big and negative, then the reaction, in many cases, we would consider that it goes to completion. And then close to delta G being 0, you get an equilibrium. Now that's not K equals 0, obviously. Look at the numbers. That's delta G is 0. Look at the numbers. K is very big here, K is very small. K is equals 0. Doesn't exist, does it here? It gets very, very small, but it would be asymptotic. This would be around K equals 1, but they're not going to really show that on this. Why? Because when K is around 1, then you've got more or less the same amount of products as reactants. Okay, lovely concepts. Right, sorry about all these equations, but you've got to see them just in case you need them. You should learn this one. Okay, you definitely need to learn this one. We can play around with that and we can say ln K, if delta G, we make it equal in both of these cases, then ln K would be that, wouldn't it? Check the maths. Now we can separate those terms, so we get that. Okay. Now, let's have a little think about this. You can write down your own notes here. But for a reaction to go forward, for more products to be made, K needs to be big. So this term needs to be big. Okay? It needs to be big. The effects of the sign of delta H on K. If delta H is positive, then that makes this term more negative, doesn't it? It makes it negative. So the total of this sum will be less, so K will be smaller. Okay? So if you keep everything else constant, if you make a reaction more endothermic, if a reaction is more endothermic, then K is going to be smaller. So the endothermic reactions aren't favored, but can happen spontaneously, but aren't necessarily favored, which is one of the reasons why chemists, early chemists in the 17th, 18th century thought that spontaneity was to do with a reaction giving out energy, being exothermic. If delta H is negative, that makes this term positive, which will increase K and make the production of the products more likely. If I increase T, that makes this term less significant, doesn't it? So if I increase T for an endothermic process, then it makes this term smaller and it makes K bigger. If I decrease T for an endothermic process, it makes K smaller. If I increase T for an exothermic process, it makes this term smaller, so it makes K smaller. Let's think about what I've just said. if I increase the temperature in an exothermic process, it makes K smaller. Well, we know that because increasing the temperature in an exothermic process makes the equilibrium shift to the left. So you get less products and more reactants. And we know that. That fits with what we've seen before. So those conclusions come from these equations, not from Le Chatelier anymore. Le Chatelier was purely an empirical relationship, wasn't it? Right, have a go at the questions on those pages, read through the text.